Let's take a few minutes to begin our study of valence shell electron pair repulsion theory. And you see here the shapes of molecules that can result from our work, or some of them anyway. VSEPR, that's how it's pronounced, assumes that the shape of a molecule is determined by the repulsion of the electron pairs within the molecule. So as you can see, there's attraction between the nucleus and the electrons in both directions, and there's repulsion between the nuclei, but there's also repulsion between the electrons, and therefore the electron pairs in the octet or deficient octet or enhanced octet, they will repel each other. Now this, for instance, looks at water, H2O, and you can see that there are two covalent bonds between oxygen and hydrogens, and there are two lone pairs on the other side of the molecule. So we'll see how we can work on this and work on the angles. So, VSEPR theory is based on Lewis structures, so you have to have a Lewis structure to start. The theory predicts the shapes of the molecules that make up compounds. It's abbreviated VSEPR, you saw that at the beginning. Valence shell electron pair repulsion. And it predicts shapes based on the electron pairs repelling either in the bonds or by themselves. So they could be shared pairs or lone pairs. And we're looking at the central atom. Electrons around the central nucleus will repel each other. So these structures, in order to assume the lowest energy situation, they have the atoms such that the electron pairs are maximally spread out. Therefore, it's very important how many electron pairs are around the central atom. So, each shape has a name, and you will need to memorize these if you haven't already. The names of the shapes, we start with tetrahedral. Now, you can see 1, 2, 3, 4 electron pairs. They're all bond pairs, and tetra, of course, is Greek for 4. So, 4 pairs. The electron shape, or the electron configuration around the central atom, is tetrahedral, and the bond angle is 109.5 degrees. In the trigonal pyramidal, you can see there are 1, 2, 3, 4 electron pairs, but there's 3 bonds, as in this ammonia molecule, and a single lone pair. The lone pair, having no proton tugging on it, as the others do, the lone pair has a little more influence on the shape of the molecule, and it pushes that 109.5 degree electron angle down a little bit, makes it 107.5. And then in water, you now have 2 lone pairs sitting on top of the molecule, pushing the bond pairs away from them, and therefore you have an even smaller angle. You know that any linear structure, as in beryllium difluoride, VEF2, is going to have a 180 degree bond angle. Now, trigonal planar, and you worked with this with magnets, have in boron trifluoride, they're going to have 120 degree bond angles because there's 3, in this case, bonded pairs. If there were one lone pair here, as there could be in an ion, then you'd still have 120 degree bond angle that might be pushed down a little more, maybe it's 118, 117 degrees. Now, you also, if you're going to have not 4 but 5 bonded pairs, like in phosphorus pentafluoride, you're going to see a trigonal bipyramidal structure, and you'll see that modeled in wood in the lab. And the octahedral angles which are 180 here and then 90 degrees around the center, the octahedral is going to be characterized by 6, in this case bonded electron pairs. Now, it's very difficult to model electron pair repulsion because charges leak off, so nobody does that. But if we use permanent magnets, as we did the other day, and if we have, as we did the other day, only north pointing out from the magnets, because we use these little cylinder magnets to make them, we can get good repulsion between the like poles. So we showed you 3 repelling magnets dangling from this pivot, this aluminum pivot, and the 3 equal repulsive forces produced what angle between the magnets. Talk to each other about that, or even turn off the video and I'll give you the answer in a second. And you saw 120 degree bond angles. It's real easy to see if you shine a bright light down on the configuration. You can measure those angles, and they're very close to 120 degrees. Now, the models that we come up with are, again, tetrahedral, so this is kind of a three-dimensional look at it. Trigonal planar, recall this when you had 3 bond or angles, and therefore 3 repelling clusters. Bent, when you had a tetrahedral shape. This is not exactly right, because it looks like there's only 1 electron pair up on this molecule. But no, this is water. There's 2 electron pairs on the side opposite to the hydrogen atoms. Then trigonal pyramidal down here, that of course also you can see has 4 electron pairs around the central atom, but one of them is a lone pair. And so these 3, for instance, hydrogen atoms are pushed away, pushed down, and that's why it makes a little kind of half pyramid here with a triangular shape. Then of course, if you've got only 2 atoms in the molecule, that's obviously going to be linear, like hydrogen fluoride or hydrogen chloride. And if you have linear structure, like in carbon dioxide or beryllium difluoride, then you're going to have just 2 electron clusters and 180 degree bonding. And here with 5, you can see it a lot easier than you did on the previous slide. You have trigonal bipyramidal, and then here you have octahedral when you have 1, 2, 3, 4, 5, 6 pairs of electrons involved. All right, we look at methane, CH4. We know the electron structure is tetrahedral, but we also can see with those 4 bonding pairs, we can flesh that out and kind of represent it in 3 dimensions, and we can see the 109.5 degree bond angle that results, not 90 degrees. Now, most of the time on a test, you're going to see it drawn like this. You all just count the bonds, and you'll know there's 4, so it has to be a tetrahedral electron structure. And if you've got 4 the same atom here, then you've got to have 109.5 tetrahedral structure for the molecule. So the bonds are all evenly spaced electron groupings, and that gives you tetrahedral molecule. Now, with tetrahedral electron geometry, you can also have just 3 bonds and 1 lone pair. Ammonia is a good example of this. And if you look carefully at it, you see there are 4 electron pairs, but one of them is a lone pair. And therefore, you have the tetrahedral electron configuration, 1, 2, 3, 4. But you have a trigonal pyramidal molecular structure. You're going to have to look at that a number of times before you'll get it. Okay, now, because of the lone pair here, this angle between the hydrogen atoms and the nitrogen is a little bit squeezed. So it's less than 109.5. But on tests, usually, they'll let you say 109, 109.5, and you can get away with that. unless they specifically ask you what that lone pair does to the bond angles down here. Now we've got water also. 1, 2, 3, 4 electron pairs around it, and therefore it's a bent structure. So you might see it drawn like this, but don't get suckered in by that. You know these lone pairs are here, so you've got 4 electron pairs pushing on each other. And there's the last 2. 104.5, again, those lone pairs up here push the angle down and make it smaller than 109.5. All right, now here we show it in a little different way. You'll see this occasionally. Try to three-dimensionalize this flat thing. You draw a kind of a wedge coming out for the hydrogen that's pointing at you, and you put these dashed lines here for the hydrogen that's pushed into the screen. Same thing over here with the ammonia molecule and the water molecule. Yeah, you don't usually have to fool with that, because it's kind of hard to show these things being anywhere but where you put them. But you know that this is a three-dimensional structure, and the lone pairs are here behind the screen and here in front of the screen. All right. So this is just a short diagram. We'll just run these real quickly, showing you the various molecules and the way you can draw them. Tetrahedral, trigonal, pyramidal, and then here with water, and its shape is bent, and carbon dioxide, of course. Now you've got 2 double bonds on either side of the carbon, so you've only got 2 electron regions here, and carbon dioxide then is a linear molecule. And finally, with beryllium dichloride, you have 2 electron pairs, 2 electron clusters, shape is linear. And with boron trifluoride, you have that structure, 3 electron regions around the central atom, and 120-degree bond angles. Trigonal plane. Okay, the next video we'll get into electronegativity and bond polarity, and we separate that out so it's easy for you to study just one or the other of these.